Hello, good morning, good afternoon, good evening, wherever it might be. My name is Sean, and I'm delighted you're joining us for today's ESPC community webinar. Today I'm joined by Alan Smith, MVP, who will cover Drop the Base with Embedding and Vectors in Azure AI Search. We love hearing what you guys have to say, so remember joining the conversation about today's webinar and more on X. Our handle is at ESPC_community and our hashtag is hashtag ESPC25. Tweet us, tag us, and tell us what you learned. Don't forget to check out our Learning Hub, which is updated with the latest blogs, ebooks, webinars, and how-to videos. You can access and view the Learning Hub by visiting our website, sharepointyourapp.com, and clicking Content tab at the top. Don't let the learning stop here. Continue to keep up and stay ahead by joining us for our next webinar. Let's leave the progress reports to the agents with Greamer. This webinar will take place Thursday, 21st of August, 3 p.m. CEST. For more information on this webinar, please check out www.sharepointeurope.com/Azure AI Week. At ESPC 25, we're going all in on AI with expert-led sessions covering Azure AI Foundry, AI agents, responsible AI, generative AI, Copilot, and AI in SharePoint. This is your chance to learn directly from top experts and Microsoft MVPs. Driving the future of AI and productivity. Scan the QR code on the screen and use the code Azure AI Week 200 to receive €200 off your ESPC 25 ticket. As always, if you have any questions at any stage, please feel free to type in the questions box and Alan will get to them during the webinar. This webinar will be recorded and added to the Resource Center, where you'll be notified by email when it is available. And now I'm going to pass over to today's webinar presenter, Alan. Hello, Alan. Thanks for joining us today.
Hi, hello. You hear me okay?
Yeah, I can hear you.
Great.
Should be able to share your screen now.
Good. Thanks for that introduction. So, as Sean mentioned, my name is Alan Smith. I work for a company called Active Solution. We're about 45 consultants. I'm from the UK, from the north of England, but I'm based in Stockholm, Sweden. I do have a YouTube channel. I'm not that good at uploading videos, but there are a few videos on there on Azure AI Search. So if you'd like to go and check those out, that gives you kind of a bit more background on how the search service works. And the main focus I've got is looking at using Azure AI Search, but really looking at working with the vector capabilities in AI Search. And I'm going to be talking about using text and audio and images as well, because vector search is something people are talking a lot about. Please be interactive. As Sean mentioned, I can see the chat window. I've got it on screen right now.
Alan, you can share your screen as well if that's okay.
Okay. Am I not sharing?
Yeah.
Okay.
There you go. Perfect.
Excellent. Yeah, sorry about that. Yeah. So a bit of an introduction. It feels like I've been building stuff forever. I started as a developer in 1995, building CD-ROMs, and I've kind of been hands-on the whole time. I've not gone into project management or architecture or sales or anything like that. I always have stuck writing code. I work a lot with training now, so I deliver a lot of Azure and AI courses, and I'm in the AI MVP program, Microsoft MVP program. Again, I've been in this, it feels like forever, since 2005. I started out as a BizTalk server MVP, and I've been through a few other disciplines at Azure for quite a number of years, and then finally ending up in AI. I've organized conferences, I speak at conferences, I've helped kids learn to code in Coder Dojos and so things. So I like to be connected with a community as well. My LinkedIn page, feel free to connect and ask any questions on LinkedIn, in LinkedIn messages. I'm happy to answer questions after the session. And as I mentioned, be interactive. Please ask questions. I teach a lot of courses online, so I'm used to getting questions, and it helps to make everything a bit more interactive. So what I'm going to be talking about is working with vectors and embedding. And the thing that got me interested in working in vectors and embedding was a project we were working on for an auction company that has an auction website. And what they wanted to do is when somebody uploads an auction item, we get the image and we get the description of the auction item. And what they were wanting to do is, based on the image, they were wanting it to put it in one of, I've only shown a few there, but there's about 26 different categories. So this image of an E-type Jag would be hopefully classified as vehicles by the AI model. We did have some issues. If you were selling a toy car, it would sometimes classify that as vehicles as well. So there were a few issues, but we did get quite good accuracy on that. Right about the same time, I was watching a YouTube session by Eric Bernhardsson. He's from Sweden. He used to work for Spotify. And he was looking at vector models and something called approximate nearest neighbors searches that we'll talk about a bit later on. And this is really the vector search capabilities that's generating a lot of buzz in the AI community now. Now, what he wanted to do was to find similar sounding music. So he developed this library for Spotify that was used in their recommendations engine. So, if you've used Spotify, it recommends music to you. And when you think about how you build a recommendations engine, if I like listening to Daft Punk and Chemical Brothers, and you like listening to the similar type of music at me, if I start listening to a new band, it's going to recommend the music that I listen to other people who share the same music tastes. But the problem with Spotify was there's so many new bands who are dropping tracks into Spotify. If a new band comes along, then nobody's listened to it. So the recommendation engine doesn't know who to recommend it to. So it gets no recommendations, so the songs don't get played. So what they wanted to do was to use recommendations, but based on if this music sounds like stuff that I'm going to be interested in. So if it sounds like Daft Punk or it sounds similar to the Chemical Brothers, it's going to recommend it to people who like that type of music. So Eric built this fantastic library called Annoy, and that's available. And the thing that really caught my attention was this section here, where he's saying you can also do vector searches based on images. So these are images of food from a data set that he's got on food. And you can see that this is the search image, and these are the actual results that come back from the search. So if you search for images, what it's doing is it's finding similar stuff. And I thought this is going to be really great for the auction site, because if somebody's browsing a particular auction lot, then we can say you might also be interested in. And instead of using just the category, we can actually find auction lots that look similar to the thing that somebody's browsing. So we got, all kinds of weird stuff, like these weird brass horse statues. And when we got the proof of concept, it would recommend other really similar brass horse statues to the one that the person was browsing. We didn't actually put that into the system. We built it on Annoy. At the time, Azure Search did not offer vector capabilities. It was quite clunky to build the index and get it deployed in Microsoft Azure, but it was interesting as a proof of concept. So Spotify Annoy, as I mentioned, it uses this, it's got the coolest acronym ever. Annoy actually stands for Approximate Nearest Neighbors, oh yeah, and that's basically the name of the library. It is available on GitHub if you want to download it. Spotify doesn't use it anymore. I think they've moved on to other technology, but I use it a lot when I'm playing around with vectors. I don't have to have an Azure account. I don't have to be connected to the internet. It's about 10 or 15 lines of Python to create and use a vector index, and it's very quick. So it's a useful thing to understand. So a bit about vectors. We're going to be talking about working in high dimensional space. When we talk about high dimensional space, typically we're talking about 512 dimensions or 1024 dimensions. And the human brain can't really understand that, but we can understand 3 dimensions pretty well. And if you've worked with, web development, any type of, graphic design on computers, you understand the red, green, blue color scheme. So if we take the color Azure, that has the byte values of 0, 1, 2, 7, 2, 5, 5. A data scientist would say, well, it's 0 at 0.51. And that's where that color fits in this 3D color space. And this is actually a vector. It's basically a 3-dimensional vector that's going from 0 out to the location where the color fits in 3D space. So we can put these colors into 3-dimensional space, and you can see that colors that are similar are in the same area. So what we're doing when we're working with vector searches, instead of using 3 dimensions, we're using 512 or 1024 dimensions, but the principles are still the same. When it comes to finding similar items within this vector space, there's a few ways of doing it. One of them is Euclidean, one of them is cosine, there's also dot product, and there's something else. So if I have the color Azure, a graphic designer would argue that anything along this line is a similar color. So this is basically half the value of this. It's got the same angle, it's got half the magnitude, but it's just a different shade of the same color. So in many cases, the cosine similarity is going to be a measure of the difference of the angles. If you remember at school, the cosine of a 0-degree angle is 1. Cosine of a 90-degree angle is 0. So the cosine, it gives us a measure of how similar the angles are within this high-dimensional space. Euclidean is how far away the points are in this space. So cyan is actually closer to azure than dark azure is to azure. But we would argue that this is a more similar color. In some cases, you may find that the Euclidean distance works better or the dot product works better. So you've got to experiment a bit with that. But that's what's happening when people talk about cosine similarity in vector databases. So a bit about how text embedding works, because if you've been working with AI and large language models and GPT, people talk about doing something called RAG, or retrieval augmented generation. And this is when a user types in a question, we go to a search engine, we search for stuff, and then we use that retrieval to augment the prompt and generate the response. So that's basically what retrieval augmented generation is. And using a vector search can be useful in some scenarios. And with text embedding, what we do is we basically use, here I'm using an embedding model. So I'm using the ADA 002, which is hosted in OpenAI, Azure OpenAI. And I've got some sentences here. So here we've got a sentence, the food was delicious and the waiter was very friendly. This is in English. And then we've got the same sentiment of sentence. The main course was excellent and the staff were very hospitable, again in English. And then I've translated, I think I used Google Translate to translate that into a few different languages. So this is French, this is Swedish, I think this is Italian that translation. So they've got different translations, but they are the same sentiment. The sentences basically mean the same thing. And then we've got 3 sentences about embeddings, and we've got 2 sentences about kids playing in a park. So if I generate this array, we can then actually work with the embeddings. So what I can do is I can select 2 texts. So I'm selecting 0 and 1. It's a 0-based array, so this is the first 2. And then I'm using the embedding model to generate the embeddings for that text. And if I run this, you can see that the embeddings for the text, this is, I think it's 1,536 floating point numbers. So it's a really big bag of these vectors. So that's what the high dimensional space is. It's 1,536 dimensions. And what we can do is we can calculate the cosine similarity, which is this line of Python code here that's using NumPy to just basically figure out the actual cosine between those angles. It's saying for these 2 sentences in English, it gets a value of 0.919, which is quite high. Now, the really cool thing about vectors is that I can go over to a different language. So here I'm using English and French, and it's still giving a good similarity. And then I can go to, I think it was 4. I'm using Italian and French, and we still got this 0.88. So this is the advantage that the vector search has over a keyword search, because all of these are using different words. This wouldn't work if I wanted to find similar sentiment using keywords. We wouldn't get good hits. But using text embedding, it's a way of being able to search based on the sentiment or the meaning of the text, which can be useful. Now, I would argue, and I've always been saying this, that these vector-based text searches are not better than a keyword search. They're just a different way of doing things. They're an alternative. In some cases, they're better. In some cases, a keyword search is going to work better. You've really got to examine for your scenario. So don't think that vector is better than keyword. It's just a different way of doing things. And you can combine the 2, which they do in Azure AI Search. So just for fun, I plotted this diagram here, which is basically showing these 5 sentences here. You can see that the cosine similarity for those is fairly close. And then these 3 sentences on embeddings, we've got quite good similarity there. And then on these 2 statements here, there's good similarity there. So that's basically what text embedding involves. But we don't have to be limited to text. We can also do this with other things. So with text, we have basically these vector search, which will find similar sentiment. We've seen that in the demo. We can also do this with images. And this is what I was planning to do for the auction house, where you can take a photo, you can vectorize it, and you can search for similar looking photos. And as Spotify was doing, as Eric was mentioning in his presentation, you can do it with music. So you feed in Welcome to the Jungle by Guns N' Roses, and it comes out with other songs that sound similar to Welcome to the Jungle, like Paradise City, for example. So my head's blocking that. So that's just showing the results there. So with image embedding, we're doing the same thing as we do with text embedding. We have a neural network. We feed the image into the neural network, and we get out a big bag of floating point numbers. And we do exactly the same thing. We search for other images that have similar vectors in this high dimensional space. So if you've worked with neural networks, this is basically what a convolutional neural network will do. It does edge detection, shape detection, feature detection, and this is kind of if you're into Python and TensorFlow and PyTorch and all that good stuff. It's very easy to be able to take a text-based network and just modify it so we get these embedding vectors out of it rather than the actual prediction of what the actual image is. So I can just show you just a quick demo of how this works. We get a load of images, we embed those images, we get our vectors, we put them in Azure AI Search, and then I can take an image, put it in AI Search, and I can find similar looking items. So quick demo of how the image embedding works. If I just switch to this this notebook, I'm not using. I am using Azure AI Search for this, but I'm not using a model in OpenAI. Because I've worked with PyTorch quite a bit, I can create an image classification model in PyTorch, which is one line of code. We put it into evaluation mode. We generate a transform to transform the images to 244 by 244 pixels and convert them to floating point numbers. And now, with about 10 or 15 lines of Python, we can do image classification. So what I'm doing is I'm taking a series of 10 photos, I'm feeding them into the network, and they're coming out with the actual predictions. So they're getting quite a few of these right. That's a German Shepherd. I think it's maybe getting confused between Labradors and other types of dogs, but it's got miniature poodle right. I don't know if that one's correct and that, but PyTorch is really easy to actually build stuff. So what I can do is I can do this line of code here, which on the slide, if I just drop back to PowerPoint, what I'm doing with that single line of code there is I'm replacing the classification layer with a layer that just gives out the actual numbers. So I'm really generating an embedding network rather than a classification network. So that is this line of code here. So the reason I show this is it is easy or fairly easy to create these embeddings yourself. You don't have to pay OpenAI for that. Who decides what each embedding dimension represents? Do the arrays always mean the same thing? No, it depends on the network. And what happens is when this happens during the training process for the network. So when they train a neural network, the neural network identifies the features. So for images, it could be something like a dog's nose or a cat's eye or a human ear would be basically one of the actual outputs in this vector. We don't really know what they are. It's something that's actually done during the training process of the neural network. Okay, so if I run that and I run that, you can see that now it's not predicting what the image is. It's coming out with this big bag of floating point numbers. And what we can do, there's quite a few of those actually. So yeah, I think it's easiest if I just whiz up here, and I think I can clear the cell output here. I can just do that. So what I can do is I can connect to Azure AI Search because I've indexed images of 12,000 dogs in Azure AI Search. So what we can do now is get a menu of dogs, and I can select dog ID 9, and I can just do a search. I take dog ID 9, generate the embeddings, and then I'm generating something called a vector query in search, and then just displaying the results. So this is the image that we're searching for, and these are similar dogs which are basically found by that. The neural network that I'm using, the default weights that I loaded up, they are very good at being able to work with dogs, because there's a lot of dogs in the training data. So this network is pretty good at being able to find different types of dogs. So if we choose a different one, I'm going to choose dog ID 4, which is the German Shepherd. And you can see it's picking out other German Shepherds. I think all of those, or most of those, are German Shepherds, or look like German Shepherds. So this is, I don't know, 50, 100 lines of Python, and I'm able to build similar image searches. It's really, really powerful stuff when we understand how to leverage those networks. So we've got this. You can also do it with faces as well. So this is kind of how the face recognition services work. So we can also do face embedding. So when I think I was speaking at a conference in Belgium, and I know a lot of the speakers in the WhatsApp. There was a WhatsApp group, so I just basically put a request out and said, "Hey, I'm building a Terminator that identifies people and identifies their threat to Skynet. Can I use your photos for this? It's just going to be a fun demo that I'm going to use in my session." And a lot of the people said yes. So I used FaceNet to generate these face embeddings, put them in Spotify Annoy, and then I can take myself and I can send that into Spotify Annoy, and that can basically recognize me. So I've got an actual video of that. If I can just go to the demo videos and bring it up, I think it's this one here. And this was in a bar in Belgium the night before the conference. And what I'm doing is, these are the speakers at the conference. You may recognize a few of these. It's recognizing the faces, and then it's using ChatGPT based on their speaker bio to generate a threat as to why there'd be a threat to Skynet. So Martin Balayo, he brews his own beer. So it's saying Martin Balayo poses the amusing dilemma of being able to get Skynet drunk on his homebrewed beer. And Rick does lots of things with networking. So it says he can crawl under the floors and cause destruction by messing around with their wiring system. I thought, this is fun. We do, when we're at a conference, we always have a stand at the conference, so we like to have something cool that was running. And I thought this could be something cool that we have on our stand, where when a speaker walks past, it identifies them and comes out with this funny quote. And then the EU AI Act came in and said you can't use face recognition in public places. So I still use this as a demo, but it's a nice way of showing how we can use vectors in other scenarios. So I've always liked music. So one of the things I thought was, well, can we do the same thing with music? Because originally Spotify Annoy was written for finding similar sounding music and doing music recommendations. So can I do it with being able to find a way to mix music together? A few years before, I got into something called Sonic Pi, which is a way of being able to write code and be able to generate music using code. This is a free download that you can go and download. And Dylan Beatty was doing a presentation on the art of code. It's available on YouTube. It's a great session. He talks about how you can use code in very creative ways. And this is one of the things that he demoed. And as soon as I saw that, I downloaded it and started playing with it and thought, well, can I use it for DJing? I started looking at a few DJs like James Hype and DJs from Mars, and thought, well, can I do what they do, but using Sonic Pi? Because the stuff they use is really, really expensive. Like, this is about €2,500 for just one of those things. And then if you want to do this, professionally, some of these people have 4 of those, and then there's another few €1,000 for the mixer. So it's about €15,000 to buy what they're working with. Sonic Pi is free. And what they're really doing with these is they're playing samples. You can see there's a sample there, which is a music, and there's a bit of a sample there, which is a bit of a vocal track. So what they do, if I can bring up the video, hopefully you can hear the sound on this. If I just show what they do, they did this mix where they put together, I think it was they mix 100 songs in 13 minutes. Hopefully you can hear that. Easy, break it, fix it, trash it, change it, melt, upgrade it. Put giants up, down it, on it, put giants up, snap it, work it, put giants up for Detroit. I love the city. Technologic. Put giants up for Detroit. I'll just stop that there because there was some inappropriate language coming in there. I thought, well, can you do that in Sonic Pi? So I started downloading the samples and putting the samples together, and then I have Sonic Pi running here, and then I put this together. I don't know if you can still hear me, but the code there is just playing these samples and looping, and I was trying to use the same stuff that they were doing. So that was kind of okay, but I thought, well, there's a couple of things that are wrong with that. It's really static. I wanted to do something more dynamic where I play around with the code and actually do the mixing live, like they were doing, actually, you know, touching things and making the mix more interactive. And I didn't want to just take what they'd done, all the hard work that they put into producing that mix, because it must have taken a long time to figure out those 100 songs. I wanted to find my own songs that would mix together. So I kind of started looking at how this works and how we can work with embedding and do similar sounding beats. So the first thing I did was to take my MP3 connection. That's just a screen from the internet. It's not my my MP3 connection. It's just some albums. And then I did the same thing as I did with images. I put them into a neural network, and I get this big bag of floating point numbers for every song, stick them into Azure AI Search, and then I can actually find the similar sounding songs. So I used to do this, this presentation previously kind of finished on this demo, but I was never really happy with how the demo worked, and I'll explain why. Okay, so this similar sounding song search, again, what I'm doing is I'm working in a Jupyter notebook. I'm connecting to Azure AI Search. And then what I can do is I can take songs and I can do the embeddings of those songs. And in this case, I'm searching in Azure AI Search. Here I'm running a search with querying, saying the artist is equal to Prodigy. And then the nice thing about Azure AI Search is it's a hybrid search. As well as doing the vector searches, we can say, you know, the artist is equal to this, and a window around the BPM, and we can select tracks of a certain key and so on, but also use the similarity as well with a vector search. So if I take track 10, which is Voodoo People, and I can search for songs that sound similar to Voodoo People. And what it's going to do is it takes a few seconds to generate all of these audio play buttons there. But the first song, the song that's most similar to Voodoo People is Voodoo People, because it's the same embedding. It's going to generate the same similarity. And that sounds like this. So the next song, the most similar song, I thought this was wrong when I first saw it, was Disco 2000 by Pulp, which then we got Therapy and Dylan's and the Pixies. And it goes all the way down to, oh, we got Oasis, oh, Sonic Youth as well, and The Jam. So it's pretty good being able to pick songs that sound similar. So I basically built this mixer thing where it would use that search to actually mix tunes together. And there's a guy at work, our tech lead, Robert. He's an actual he does a DJing. He gets paid for it, so he's pretty good. And he was very, very polite. He says you might be able to use that in a bar for mixing background music and things like that, but it wasn't really that good. Yeah, a question: beyond musical beat signatures, what other conventional data types could benefit from vector indexing in AI search? IoT signals, DNA sequences. Yeah, I'd say all of those can be used. The thing is, can you convert it? Can you embed it? Anything that you can embed and convert to a series of floating point numbers, then you can use that with a vector search in AI search. So there's really a large number of different scenarios that you could use. Definitely IoT signals, DNA sequences, finding similarity there. As long as you can convert it into a one-dimensional array of floating point numbers, it should work fine in a vector search.
Alan, did you see that question? I'll put it in again. I don't know if you saw it or not.
Is anybody knows what token 000 is in any of these embedding models? No, I'm not sure on that. The embedding is also used for tokens as well. Yeah, I forgot to show this demo. If we jump into this thing, which is the TensorFlow embeddings projector. Now this is, I think it's like 10,000 words, and it's word embedding. And word embedding is kind of a key part of the way that these large language models will understand what words mean, because similar words will have similar embeddings. And what this is doing is something it's unsupervised learning, and it's doing dimensionality reduction. It's converting those 200 dimensions into 3 dimensions, so that human brains can navigate and understand them. And if I pause that, what we should see is that these are kind of clusters. All of these are relating to food. So you've got vegetable, bread, pork, cheese, and so on. And here we've got congregations, Presbyterian. These are kind of all like religious words that are grouped into this cluster here. And then around here, we've got names like Steve, Rick, Doug, Tom, Dennis. We've got male names, and this is the way that the large language models do basically understand. So embeddings are useful in so many scenarios. So back to the music. It wasn't really similar sounding beats that you were interested in as if you want to mix tunes together, because it's not going to sound too great if you mix kind of like 2 guitar intros. You kind of want to have one piece of music that complements another piece of music. You want to say, you know, a bass line that will fit onto a particular synth riff or a particular vocal track, and they don't sound the same. They sound different, but they're complementary. So that's kind of really what I was searching for. So starting getting into a bit of music. If you've studied music, you may be aware of something called the circle of fifths that was developed in the late 1600s, early 1700s, that said that certain keys have, you know, they use similar notes, or they're compatible with each other. They can work well together. So one of the examples is like C major. If you play C major, that's all the white notes going from C up to the next C. And then A minor is basically all of the white notes going from A up to A. So C major and A minor use the same notes. And that's the same for all of these minor and major combinations. Now this is a bit complex, so it gets simplified for DJs into something called the Camelot wheel. And this basically says the rule is that if you're playing something in G major, then the compatible songs are going to be E minor, C major, and D major. So this is where you should be looking to find complementary music. Then you can do something called harmonic mixing, because Sweet Dreams by the Eurythmics and Enjoy the Silence by Depeche Mode are both in C minor. They're different BPMs, but what I've done is I've speeded up Depeche Mode, I think, to the same BPM as Sweet Dreams. This allows you to just do something called harmonic mixing. You can kind of have harmonic similarities. So I shut down Sonic Pi. I shouldn't have done that. I'll just start that again. So what you can do is put the lyrics or the vocals. This is a track, Annie Lennox. Sweet dreams are made of. So that's an a cappella track, and then we've got the synth from Enjoy the Silence, or one of the synth tracks. This is on YouTube. They've got the like kind of the studio old stuff from Enjoy the Silence with all the separated stuff. So you can basically put those two together. Who am I to disagree? I travel the world and the 7 seas. Everybody's looking for something. Some of them want to use you. Some of them want to get used by you. Some of them want to abuse you. No, that's kind of stuff that DJs from Mars do. They'll put the vocals of one track on the actual music from another track. And then I started looking to do this, and it's really, really hard to find these matches. It took me a long time to find this one. It was taking so much time to find these. So I thought, well, can we actually do something to actually, you know, help to speed up the process, which is kind of what I was focusing on here. So finding mixing phrases. What I do is, again, I've taken you know, a bunch of MP3s. I've put them into DJ software, which is called Recordbox. Now, Recordbox is a free download. It's what I think there's a couple of them. There's something called Recordbox, and then there's something called Serato, I think, and most people will use one of these two. I don't know if Serato's free, but you can certainly download this. And if you're into music, it's kind of a nice way, if you're old enough to have an MP3 collection like I did, it's a nice way to play MP3s because it gives you the option to, you know, modify the pitch, modify the tempo, play a couple of things together, and you can spend anywhere between €100 and €300-400 and buy a sort of fairly basic USB controller that gives you the option to, you know, just start experimenting with DJs. So if I go to the tracks, you can basically drop on so the Belt by deadmau5. One of the things that Rekordbox does, or the reason that I'm using it, is it's able to extract information from the music. So we get that the Velt by deadmau5 is, what's it saying, 128.1 BPM. It's showing us the beat grid, which is showing us the 1, 2, 3, 4 on all of those. And then we also get the phrases. So they've got the chorus starting here, and I can go to a particular section in the song and say, well, if I want to just play this bit, then that's going to be that particular section in the song. Now, all of this information is really, really useful. I want to know what key this is in. I want to know where all of the beats are. I want to know where all of these particular phrases are, because I want to combine the phrases from one song with the phrases from the other song. So what I do is there is some code. The people who built Rekordbox, they did their best to make it so you can't access the data. They've encrypted the database. They've done this really complex file format, but developers are clever. They figured out the key for the database. They figured out and reverse engineered the file format. So there are libraries in, I think, in Python and Java that you can use for being able to access that information. So I get all of that metadata and I generate a JSON file that contains that. This allows me then to generate the embeddings, which I do not just for the single song, but for every phrase in the song. And that gives me the embeddings, and then I can split the tracks into separate MP3 files, one for each phrase, because we've got the beat grid and we've got all the timing information, and you can use that to programmatically generate the MP3s. And we can also, they've figured out when they reversed engineered it, how to get the actual waveforms that are displayed in the DJ software, and that's useful when you're comparing tracks, as we'll see a bit later on. Then we can drop all of this information into Azure AI Search, and I can search for similar sounding music. So the phrases we'll get, typically this is how it looks like in Azure AI Search. We get the artist, we get the title, the key, the BPM, and also it gives us these labels. So we've got whether it's, you know, kind of a, you know, decreasing in intensity or increasing in intensity, and then the number of how much it's increasing in intensity. So this is really, really useful information that we're going to need during the actual search. Then it comes to the embedding of the phrases. Yeah, I can actually drop, I think, into Jupyter Notebooks. It's going to be more fun to show this as a demo than the actual slides. So if you look in the music theory one, I can run this and I can choose that track, which it was Alan Walker, I think it was. So if I get the phrases from that, and I think the phrase I'm using was I think it was no, it was that phrase I was using. So I choose phrase one just to analyze. We get a couple of things coming out now. This is a Mel spectrogram. You'll have seen this if you've played around with music software quite a bit. It's showing a frequency versus time. And if I play the track, it's really hard to see how this relates to the actual music. It's quite complex. But another thing that you can do as well is generate the actual chroma information, and what this is showing is the actual musical notes that are dominant within that particular phrase. So if I run this, sorry, I need to just start this from the beginning. It's showing the bass, the chord progression. Can you make me feel better? So what that's giving us, this is what I use for the embeddings. And you can create this using a bit of code, using a Python library called Labrosa. It's fairly easy to be able to generate this chroma information. I think the code is up there or something. Where is it? Yeah, this is the code where I'm basically generating that chroma filter from the signal. It's a few lines of code. Now, if we search in Azure AI Search for something that is similar to this, then we're going to get music that has this dominant chord progression of like F, E, A, and G, and then that's hopefully going to match with that particular song, and that's how we can actually do our searches. So I'll draw back to the slides. I think there's a bit more theory, and then we go into the demos. This is just basically showing the same thing that I was showing in code. Now the embeddings, they all have to have the same number of dimensions, and the phrases are different sizes. So what I did was I took 32 beats from the beginning of the phrase, and so sometimes it does include the section for the next phrase. Sometimes if it's a long phrase, then we only get the first 32 beats, but it seemed to be the best way that I could figure out of actually doing these searches. Do you see a future where hybrid search, keyword, and vector becomes the default rather than optional? I think that's what Microsoft is focusing on with the Azure AI Search technology. I had a talk when I was at the MVP Summit with Pablo, the project manager of Azure AI Search, and he seemed to think that, a lot of companies were using these vector capabilities. And we found that sometimes vector isn't the answer. I was actually working on a project. This was something that was built by another company to do job searches, and they'd built everything on vector search and it didn't work too well. So we built a proof of concept that was only using keyword search, and it worked much better than the actual vector search solution. So I see having the option to choose keyword or vector or hybrid is really the best option there. Then you can experiment with different ways of being able to actually do the searches. So when it comes to mixing the phrases, the stuff is typically different beats per minute. So here we've got Better Off Alone by Alan Walker. We've got This Is What You Came For by Calvin Harris. The BPM doesn't match. Now, in the olden days, when people used to DJ with vinyl, they'd have a couple of Technics turntables and they'd have like a slider on the side. And what you could do is you could move the slider. And so you're actually getting the beats synchronized. But when you did that, that also changed the pitch of the record. So it's really, really challenging to be able to, do seamless mixing using vinyl. They make life easy here because you've got this button called Beat Sync. Some people call it Cheat Sync. And you click on that, it synchronizes the beats, and it also doesn't change the actual tone. So you can change the tempo without adjusting the pitch, which is important if you want these songs to fit together. So I have to do that programmatically, and I'm doing this in Python using a library called Rubber Band, I think. So when we get to samples, to mix them together, what I do is I will stretch one of the samples to get it into the same BPM, but still preserving it and keeping it in the same key, so that we're not going to adjust the tonality of that. So the mixing process, we've got this meta file. I select a track, and then I go in and I select a phrase. I can preview all of the phrases and see the waveforms. Typically something that's very red will contain a lot of bass. Something that's very blue will contain a lot of treble. So you may want to choose, a bass and treble and mix those together and to combine them. And then you can select the phrase, and when you're doing the mixing, it queries Azure AI Search to find music with compatible keys, and it actually creates the MP3 files for the mixing and then allows you to preview those. So the demo for the music embedding, I'll just bring up that. And what I've found with this is that it doesn't always give good predictions. I can show a kind of an example of how I work with this tool. If I run this, then I should be able to select what we can choose. Yeah, let's choose the Alan Walker track. So this gets the phrases, and this is the music with these coming from record box. Oh, I think that's all music. So if I choose phrase 1, and then we've got the options here. Do we want to use embedding, or do we just want to search for compatible keys? I'm using embedding, so it's going to find the nearest neighbors. Do we want the same key, or am I not concerned about the key, or do we want to use like the vertical keys or the horizontal, or vertical and horizontal within the Camelot wheel? And there's a bit of coding for that. And then I do at the top, I've just kind of hard coded the Camelot wheel here. So it's using that for the actual key information. So I'll keep things simple and just search for stuff in the same key. Then when I do mix, what it does is it just basically finds the compatible songs. It shows us how these are going to match with the waveforms, and then I can play, this is, and then this is the second one, and then the mix, and most of them sound terrible. But what this does is it makes it more productive in being able to find something that will work. So I typically choose something, and then you can usually tell fairly quickly if something is going to work or not. And I have found a few that do work, but I can't really demo the actual process of doing that because it's so hit and miss. And I was giving a presentation at work yesterday, and you know, when you try to do something at home, it works fine, and then when you do it in front of lots of people, it doesn't work so well. So I have actually put down a few of them that I have found previously using this tool. So one of them that did work quite well, and it's all subjective, some people may think it sounds terrible, was BBE, 7 days in 1 week. And then this was starting at bar 49, I think, which is that's going to be phrase ID 8. So I select that and do the mix. And this seemed to work well with Natural Blues by Moby. So this is the original. That's very, very bassy. And then Natural Blues by Moby. It sounds similar. It's kind of got the bass beat with this synth, and then there's other sections of that. And then another one that seemed to work quite well was ATB, 9 p.m. And that worked well with Project T by Dimitri Vegas. So which phrase was I was choosing? Bar 17, so that's phrase ID 2. And run that. And that was Project T by Dimitri Vegas. It seemed to work well with. So let's see if that's this one here. So yeah, this is the and then Project T is and that's kind of a build up, so it's increasing in intensity because that says up on it. That's where it's got. And that's the mix. Then I bought Depeche. I don't think I bought. Yeah, I bought Depeche Mode's first or second single, I think. So I've always been into their music. I saw them a few months ago, and where are they? Yeah, one of the fairly recent songs, Ghosts Again, starts with this really great guitar by Martin Gore, which is this. I thought it'd be really nice to find a dance track where you can actually use the guitar from Ghosts Again. So if I take 0 and just do that mix, and that was coming up with this. You got me up and I'm waiting for the truth. You left me helpless now. Now it doesn't sound too great on its own, but if you could find the a cappella for this, where you've just got the vocals and get rid of all the other backing music, and then just have that guitar from Martin Gore, it would probably sound nice. And then another one again, Depeche Mode. That was, I think, where was it? I think it's Everything Counts. Let's find that. And that went against, what was he using? Bar 11, so I think that was track 3 or phrase ID 3. Just do that mix. And that kind of worked well with Jack Jones, I think, if we can find that. And after a few hours of playing around with it, I did find a few more things that did actually work. So I put these into Sonic Pi. So this was Again, Depeche Mode behind the wheel with Let's Go Dancing by Tiga.
Let's go dancing. I wanna go dancing with you all night dancing. Let's go dancing. I wanna go dancing with you all night dancing. Let's go dancing. I wanna go dancing with you all night dancing. You're behind the wheel. Let's go dancing.
And then this was combining 3 tracks. So there's 20 Years on Acid by Kate Lawler, Faded by Zoo, and again 9 PM by ATB. And then this was a bit more complex. I'm actually using a filter here to modify the cutoff of the track. I don't know if you've done or played around with any of these DJ systems. They're really fun to work with. The stuff that they have in the middle, if I can find the photo, all of these things here, they basically do the EQ. So you can basically filter out the bass or filter out the treble and do various filtering as you're mixing tracks together. You often see DJs twiddling those knobs. That's what they're doing. So you can actually do this in Sonic Pi. I'm using this filter here. I think if I bring that out, what this is doing is it's just fading in the intro from Titanium using a cutoff of 40 and then progressing up to a cutoff of 120. So that does the fading of that track, and then you combine that with and there I think I'm playing 5 different samples at once, and that limit, if you'd spent your €15,000 on 4 decks, you could probably play 4 tracks at once. Maybe you could add additional samples on, but Sonic Pi you can just play as many samples as you want. It's fairly easy to code up. The coding language is Ruby based, but it's fairly simple to learn that. And then I was looking at, this is Coldplay, A Sky Full of Stars, combined with the a cappella or the vocal track from Rihanna, and then it goes into again the personal. So that's experimenting about how you can kind of transition from one song to another using this. So this, I'll summarize in a bit and talk a bit about the challenges, but the thing I really like or enjoy personally about working with this project is there's so much. I was always a maths geek at school and science geek, so I really like working with, Fourier transforms that we did at university and doing stuff in the frequency domain and maths and embedding and cosines and high dimensional space. That's really cool. But then the music stuff kind of just brings in this creative aspect where it's not just about maths and code and logic. There's also, the emotion of how music makes you feel and what sounds good, what makes you feel happy, and how you can use, the maths and the music theory to be able to create something that hopefully is going to sound nice. And that's why I kind of spend probably way too many hours than I should do playing around with this project. So pretty much all the software I've shown is free. Rekordbox is free. If you've got a big library of MP3 files, you can use that. Sonic Pi is free, so it doesn't cost anything to do that. I'm also using the free tier of Azure AI Search. So this is just basically running on the free tier. Yeah, this is just showing kind of how the search syntax works. If I just zoom in on that a bit, I'm selecting where we've got a BPM range and the key is equal to B minor, and that allows you to search and just bring back the actual JSON. So that's really what I'm doing, and then just adding on the vector search to kind of order these by similarity. when I'm doing the actual search. And if for whatever reason you can't create an Azure account and use the free AI search, you can use an AI to be able to do something fairly similar, and that's a few lines of Python to get going. I'm just going to round off now a few of the challenges that I had working with this project. Oh, another question, what's the cost implications of maintaining a large-scale vector indexes in AI search compared to traditional keyword indexes? So the vector quota does add a bit of data to your search. So if I go and look at the indexes that I'm using and go into the indexes, you can see the kind of total storage quota and the amount that I'm using for vectors. I think that's just the documents that I'm storing and the other indexes, and then that's a vector. So in these two cases, I'm using more in the actual the vector quotages. What I've not experimented with is there is a way to be able to do optimization of vectors, so they can identify the most useful vectors, and I think they can do about a 95% compression on the vector space compared with uncompressed, and that only gives you kind of a small impact on the actual quality of the searches. That's not something that I've looked at. So I mean, yeah, it is adding, in my case, it's about 50% of the storage is vector. So it would maybe be double the cost to use vector search as it is using keyword search. But I've not really looked at how that's going to work with large projects and with other scenarios. I think for many cases you're really concerned about the quality of the answers that you can provide, because the Azure search capabilities is going to be a small part of what you're paying for your running all your GPT models and hosting other stuff like that. And I've found when I've been doing retrieval augmented generation, the retrieval bit is critical. If you don't put the right information into the prompt, then the large language model will generate, it won't have the information to generate the correct answers, and you won't get good answers from it. So it is a really big part of the RAG, retrieval augmented generation, is just getting the right information into the prompt, and vector definitely helps with that. Oh yeah, one thing I didn't show you, I can just show this quickly, is I can actually load the music embeddings into the embeddings projector, because I've got them as a TSV file. So if I bring in the tracks here, this is a really cool visualization, because what I can do is I can label by the phrase, and then I can color map by the key. And what that shows is the different, each key is shown by a different color, and we can do the dimensionality reduction in that. I think it's really cool to kind of, I sometimes use this for finding similar songs, because what we do, just as you had with similar words, you've got these similar phrases that are grouped together. So if I just like pause the rendering, we can go in here, and you can kind of see these clusters of songs in the same key. So orbital chime might work with symphony, or this track here, or Cherry Moon, or Raise Your Weapon by Deadmau5, and so on. And then over here we've got different keys and songs here. So this is a nice visualization. Again, this is just a website. You can go in to this website here. I'll just drop that in the chat actually. So if you do want to play around with the embeddings projector, there are some samples that you can use. Another interesting one that you can play around with is the is it this one here? Handwritten digits. I might have chosen the one wrong. Oh, yeah, that's the wrong one actually. It's this one here. Yeah, so this is that handwritten digits library, which is something that you usually start out with when you look at image classification. And what happens with this when we run the dimensionality reduction is it's looking at the pixels of these. I think they're 28 by 28 pixel images, and what we see is similar clusters of similar digits. So all of the ones and all of the sevens and the twos should actually cluster together. And it also is a nice way of being able to analyze data and seeing, well, can a machine learning model tell the difference between these various digits? Already you can kind of see we've got the ones appearing over here, and the zeros here, and the twos here, and the nines, and you do see some like similar things like fours and nines appearing close together. But it's a nice way of being able to visualize that stuff. So just round off with a couple of challenges. One thing was the amount of hard drive space. I was actually running performance monitor on my F drive because I kept running out of space on it. And that was when I was kind of labbing 333 gigabytes over 250,000 files. I was generating all of this embedding files and waveform and phrases files and doing different tests. It was a stupid amount of hard drive space. And then again, Dylan Beattie. I used to teach a lot of BizTalk courses. BizTalk server is an integration server. And I've always said integration is a messy business because we have to deal very often with text files. And as Dylan is saying in this presentation, there's no such thing as plain text because you've got all these weird characters. And this thing drove me crazy. I don't know if you know what these 5 characters are. They look the same in Word. If you've got different font spacing, they look fairly different. In Visual Studio, they look exactly the same. They're actually 5 different characters. So normally you have the artist, and then we've got like a hyphen, and then you've got the track name. So that's how I extract the track names. However, sometimes they use a hyphen or a minus sign or a non-breaking hyphen or an N dash or an M dash, and I'm struggling to find out why I'm doing replace and split by this, and why isn't it doing that? Because they're using an N dash instead of a hyphen, or minus sign instead of a hyphen. So yeah, that drove me crazy. Also, people with like weird characters in the songs, that kind of messed up the filing system of it. So I think I'm out of time. It's probably lunchtime for most of you. I've got a bit more research to do. There is a database which has chord progressions of 666,000 songs. That's probably going to be useful for identifying chords. I've not had time to look into that as well. And then white papers on doing this, detecting drops in EDM using social media. So they're going into SoundCloud, looking at where people comment on dance tracks and trying to identify the drops, or where it builds up and then drops into another section of the track. So that's some interesting stuff. There's other people doing this type of work. So thanks for tuning in and thanks for listening. And yeah, there's another question.
Yeah, there's another question there.
How do you balance embedding size dimensionally against index performance and query accuracy? Yeah, it's just experimentation. I just chose that I was going to be using in the music example. I think there was, what was it, 12 musical notes, and then I'm like 32 beat samples. So this is a more high resolution one. I was using like I think one for each beat. So I had this 32 by 12 index. I forgot what the dimensions are. It's 32 times 12. What's that? 384 for dimensions in that vector. And I could have done it by half beat or by quarter beat, and that would increase the size of the vectors. Would it increase the query performance? Maybe. So it's really a trade-off there. With the text embedding models, normally when you're using the adder, it's kind of fixed on about 1,500 dimensions, and depending on the model you're using, that's going to generate more or less vectors. But if you do want to reduce the vector size, then explore the vector compression in AI Search. That will give you good compression and may not affect the results too much. Okay, I'm happy to stick around for a couple of minutes if there are any additional questions. As I mentioned, feel free to, if you think of something later on or you want a bit more information, then feel free to connect to me on LinkedIn. I think that's my QR code for LinkedIn, or there's probably going to be lots of people called Smith, so maybe it's easier to use the actual code. But I'm happy to take questions in LinkedIn chat if you got something, or if you want any more information about the software that I was using or the techniques I was using. But thanks for tuning in, and as I mentioned, feel free to ask if you got any questions, and enjoy the rest of your day or morning or evening.
Perfect. So yeah, I think that's all the questions, Alan. A few questions in. So on behalf of the ESPC community, we'd like to extend a big thank you to you again, Alan, for taking time out today for this webinar. We really appreciate it.
Yeah, it's been good. Thanks for the opportunity to present. It's something that I love working with, and I enjoy talking about. So it's been great to share that knowledge.
Perfect. So that's the end of today's webinar. You can find this webinar and more at sharepointeurope.com/research center. Thanks again for all of you joining us today, and I hope you join us again soon. Take care.
Bye.